Good evening and welcome to a Maglab Science Night with the LeRoy Leon County Public Libraries. I am Miss Casey from your LeRoy Leon County Main Library, here with our awesome scientists from the Maglab who will be talking to you about electricity tonight. So it's going to be an electrifying evening. So without further ado, take it away, Miss Yulia.
Thank you, Miss Casey, and we are so excited to have you all. Welcome to Science Night. We're here tonight with Miss Casey and Miss Kristen, and also Sujana, who is our special guest tonight. She's an electrical engineer, and I thought that would be super fitting for electricity and talking about that tonight. So we have an expert with us, and later on you can ask her questions, and maybe she can help us out throughout the class as well. So let's get started. To start, I'd like to make sure that we have everybody on board. So we'll launch a poll for you guys. Oops. We'll launch a poll for you guys. All right. And we would like to make sure that everybody can see and hear us okay. And we want to know if you can find a chat box, because we will need that. So the chat box, if it's not readily visible, you probably have to click on the 3-dot menu and find a chat box there. Also, we would like to know how old you are so that we have a little bit of an idea who we're dealing with tonight, and also where are you joining us from Tallahassee, the Big Bend area. Sometimes we have people from outside Florida. We even have people from outside the country. So let us know where you're from. I'll give you another couple of seconds. All right, I think everybody voted. All right, I'm glad to hear that everybody can see and hear us. Chat box, great. All right, we have 1 participant, 4 or 5, 2, 8 to 9, and then 2 in the 12 to 18 years range. Well, welcome everybody. And everybody is local, so yay, Tallahassee. Okay. All right, let's get going. So we'll need the chat box right away, because I would like to ask you guys, what is electricity? So does anyone have an idea what electricity is, or what it can be used for? Or do you have any experience getting zapped, maybe stepping out of a car? Anything you would like to share about electricity? And just, to give you some pointers, I have some pictures for you guys. Any idea electricity? What is electricity? Because that's what we would like to explore today.
We're getting a few answers. Any other thoughts? Okay. So we have someone who says the motion of electrons, and someone else says electricity is lights, static, lightning.
Okay, that's very good. We'll talk about that today. All right, exciting. Let's roll with that, and let's start with static electricity. So to start, as often in science, we have to zoom in and look at the very small building block level of everything around us. So saying that, all objects around us are made up of atoms. And we have talked about atoms a lot in this season. And I have a schematic picture of one here, and you already see little pluses and minuses, and they relate to charges. So there's a lot of plus charge and neutrals in the nucleus of the atom, and we don't really deal with that for the electricity, but there are electrons, and these are really the main players when it comes to electricity. And so it's important to first realize that all things are made up of charges. And for static electricity, very similar to what we talked about with magnets last time, opposite charges attract and like charges repel. So opposite charges want to be together, but like charges can't stand each other and just want to get as far away from each other as they can. However, most of the time, as you know, all the objects around us, they are neutral. You don't really get zapped when you pick up a pair of socks. So everything is electrically neutral. And as our little buddy here is telling us, the charges are balanced. So there's the same number of positive and negative charges in objects. So static electricity comes about when that balance is disturbed, when it tips. So when there is either more positive or more negative charges in an object. And we have a cartoon for that here, where in this object on the left side, there's more positive charges. And then in the object on the right side, there's more negative charges. And let's see, I want to launch a poll for that and see if we're all on board. Oops, can't poll out here. So our poll is, what do like charges do? Do they repel? Do they attract? Do they multiply? And then most of the time, the charges in an object are excited, balanced, or alike. So far we have one person voting. Let's see if we can get some more. What do like charges do? Do they repel or do they attract? We just talked about that like charges. Yeah, I don't see the answers coming in. Awesome. Okay. All right. I think we're gonna stop the poll here. Almost everybody voted, and I'll share the results with you guys. So like charges indeed they can't stand each other. They want to be far away from one another. So that's a good answer. And most of the time, the charges in an object are balanced. Only when it comes to an imbalance do we get things like static electricity. So why does that happen? So we said all materials are built from atoms. However, some materials, based on their properties, have a more powerful pull on their electrons. So they hold their electrons much tighter than other materials. So if two different materials come into contact and one has a harder pull on electrons than the other, electrons can be jumping from one material to the other. So here we see the balance situation. So we have an equal number of like the positive charges in the nucleus and the electrons around it. So the object or the atom is balanced. However, now if it's different materials and one atom pulls harder on their electrons, on electrons in general than the other, electrons can move from one material to the other, and that can create an imbalance of charges. So after this atom on the left here stole all these electrons from the poor guy on the right, this one is left with more positive charges, and this one has more negative charges. And this is where static electricity comes from. Okay, let's see how that is going for us, and let's see what you guys think about this. There's another poll for you guys. True or false? Some atoms have a more powerful pull on their electrons than others. Is that true or is that false? And then if we put two materials together and one attracts electrons more than the other, can electrons be pulled from the material that has a less strong pull on their electrons into the other one? What do you guys say? Let's see. Let's see what's coming in here. Oh, so far it's very balanced, but we have some more votes coming in. All right, I need a couple more voters here. So is it true that some electrons have a more powerful pull than others? All right, let me end this poll and share the results with you guys. All right, so some atoms have a more powerful pull on their electrons than others. That is true. And that can result in when two materials come together and one pulls stronger than the other, that it actually can steal electrons. All right. So that brings us to our first hands-on experiment where we want to try this. We're going to steal electrons from one material to the other. So this is where we need our balloon. I have a pretty pink one here and I already blew up a yellow one. And what we would like to ask you to do is stick the balloon to your hair, your shirt, or whatever you have in your house. Some places it sticks to the wall. Try and stick it to the curtain. So I'm going to start working on this, and I hope you all will do the same. So my balloon is already sticking to my hair here. And I also have some pictures for you here. So they can stick to walls, they can stick to cats, and try it out. If you have very short hair, the sock can also help you. So,
Julia, we have someone in the chat who says they have no balloon. Is there something else they could try to do
Yes,
this
you have
hands-on experiment?
yes, you have to stay put for just a little bit. And then I have an experiment for you with the spoon. Or if you already have a spoon, you can try and rub the spoon really hard and see if it wants to stick. But it depends on how much hair you have and how heavy your spoon is, if that wants to work out. But if you have a spoon, a plastic spoon, then we're good to go in a little bit. So I'd like to for people to put in the chat if this worked out for you guys. And also I suggest that later or possibly if you have a lab assistant to help you out now, you can take some pictures, and we ask you to send pictures in. If you send your picture by Monday, that's the 29th by 8 a.m., you can enter for a chance to win another cool Science Night prize. So Kaylee, I know I'm counting on you because you always send me a picture. So I'm excited for that, but I encourage everybody else to also take pictures of their experiment and send them to us.
I have one person telling us it's working.
That's exciting.
Fantastic.
So,
and if mom and dad want to share your pictures, in addition to sending them, you could always share them on the Maglab's, social media channels and stuff too. We're on Instagram. Mom and dad should do that though, okay? Unless you're old enough to have your own accounts, I guess.
All right, so while we're all rubbing balloons on our hair, I just wanted to point out that what is happening is that, the balloon is basically picking up extra electrons while the hair then is left with extra positive charges. And we just talked about, charges that are opposite wanting to attract to one another. So that helps us out with one object being negatively charged and one object, so us or our hair, being more positively charged, and they want to stick together. All right. So that brings us to the next experiment, and that's one that you guys can try out. And it's also, it's a very low hazard experiment. And I just want to say that we often get questions, do you have ideas for science fair experiments? And can we do anything with electricity? Because it can, we don't want to do anything dangerous. Well, working with the static electricity that you can make from, rubbing a sock on something is super safe. And there's lots of stuff that can be tried out for different science fair experiments. So pay good attention, and this is a nice one you can also try at home. So, so you can probably see in the picture, this person or child, I think, has a comb in their hand, and it looks like the water here is somewhat bent. So I want to show you guys an experiment with that. So you need your spoon, and you need your sock, and you need to be rubbing just like the person in the picture. You rub the spoon really, really good with the spoon, and you can move the water with it. I'm going to replay it, and I'll ask you to put in the chat what you guys think is happening here. Why is the water bending? Why do you guys think the water is bending? How can we make the water bend? Think about the charges and what happened with the balloon, or what happens with the spoon when you're rubbing it. Some materials give up their electrons more easily than others, charges jumping back and forth. So any ideas what might be happening?
Well, we have a couple of guesses. Someone says they think there are the same charges in both the spoon and the water, which could cause them to repel. Someone says because there are things that go opposite.
All right, that's a really good one. So basically what we're doing with the spoon and the sock is that, we charge one flavor of electricity and one the other flavor. So one is positively charged and one is negatively charged. Basically, the one that's positively charged is positive because it gave up its electrons readily. Said, hey, here you go. You go and take my electrons. And then as you bring it closer to the water, you can push and pull that around as you say, with opposite charges, attracting and like charges, pushing each other away. All right, there's another experiment that is very similar, and that is one that is also super fun to try at home. And there is many different things if you want to do a science fair experiment that you can play with, and I'll comment on that after we watch the video. All right, so here's what you can do. So you need your salt, your pepper, your plastic spoon, and my favorite sock, and you start rubbing the spoon really, really, really good. So you have charged up your spoon, and then you can pick up some of the particles. So my question for you guys is, why do you guys think the pepper is jumping up? And most of the salt, some salt is jumping up, but most of the salt is staying down. So what's happening here? Why can I separate salt and pepper in this way? Any ideas? All right, why does the pepper jump to the spoon?
I've never seen this and I'm amazed. Amazing.
All right, I say Kaylee says because it's lighter, question mark. That's a really good part of it. Yes, it's jumping up much more readily than the salt because pepper is much lighter. And if you watch it real close, you see some salt jumping up, but once it makes it up, it's already so heavy, it starts falling down again. So yeah, that is really good. And I see the charges of the pepper are opposite of the spoon, so it's attracted to the spoon. Awesome, yes. Yes, awesome. That's exactly what's happening. And for those of you that are interested in science fair experiments, something you can try is you can see how much pepper jumps up if you rub your spoon once, 10 times, 100 times. You can play with the distance of your spoon. So there's all kinds of variables that we can change in an experiment so that you can, design your hypothesis, take your data, and have a good project to present. All right. So we talked about like charges and repelling, and we talked about opposite charges attracting. So one other thing we want to talk about, and that you already mentioned at the beginning, which was super exciting, is that what happens when those charges build up? So if they build up on the surface of an object, it can happen that there's so much of one type of charges, and we said that they repel and they don't want to be part of each other, that they will actually discharge, and that the energy will be released in that way. And there is one really impressive example of that, which is lightning. And I'm sure living in Tallahassee, you will have plenty of experience with lightning. And maybe already that there's lots of different discharges in lightning. So lightning occurs when part of the cloud is charged positively and part of the cloud is charged negatively. And depending on how many charges they are, there can be a breakdown, a discharge inside a cloud, or even from one cloud to the other, or coming down to us. So that is what is going on there. And I always find it fascinating that within one cloud, there can be one part that is positively charged and one part that's negatively charged. And it's actually quite interesting how that happens, because it's not so different from the spoon and from the sock, because basically what happens is that hail droplets and more ice crystal droplets, like the hail is heavier, just like, the salt particles, and the snowflake crystals are lighter. So they go opposite directions and they touch each other, just like the sock touches the spoon, or just like, the hair is rubbed on your balloon, and, they can strip charges off of each other that way, and positive charges end up at one end of the cloud and the negative charges end up on the other end of the cloud. And then even if there is enough built up, there can be those discharges that we saw inside the cloud, from cloud to cloud, or from the cloud to the ground. And just since we're talking about lightning, and lightning always comes with this super impressive thunder after it, I wanted to mention that, when such a lightning happens, there is so much energy happening, energy release going on, that, there's a very fast heating of the air that's close to the cloud and the lightning. And that has a lot of, heating of the air and then cooling off the air. So there's a contraction and an expansion involved there. And that creates a sonic shock wave, which gives us that impressive thunder after our lightning. But back to electricity. Let's see what you guys think about this. All right, I launched another poll. Where can lightning occur? So there are different options and you can always pick more than one. So it can happen inside a cloud, it can happen between clouds, and it can happen from the cloud to the ground, which is, I think, definitely the one we see the most often. And then which of these conditions are needed for lightning? An electrically balanced cloud, or part of the cloud is positively charged and another part is negatively charged. Let's see what you guys think. All right, almost everybody has put in their vote. Let's see. Let's launch this poll for you guys. All right, where can lightning occur? Inside a cloud, between clouds, and from cloud to cloud. Well, I have good news for you guys because everybody is right. And then which of these conditions is needed for lightning? Yeah, you guys are all correct. We need part of the cloud to be positively charged and another part to be negatively charged. Okay, awesome job, everybody. So that brings us to hair rising science, and we already made the balloon stick to the hair. And I don't know how it was for you all, but for some with the longer hair, my hair was standing up afterwards and I had some trouble getting it back down. There is a machine that does this really efficiently, much more quickly and much more efficient than our balloon rubbing. And we have some pictures here of kids. This was when we were still at the bookstore. So you can see that everyone's hair is standing up. So what this machine is doing, and I'll show you this in a video in a second, is that it is a machine that creates lots of positive charges on a bulb by rubbing basically a rubber belt, which is the equivalent of our sock, and picking up all the extra charges with this little brush from a roller here and accumulating them on a sphere. But we have a nice animation for you guys to see this. So watch the belt here moving around, and it brushes across the brush, which is just like brushing across the spoon. So lots of electrons are being given up here, and they are picked up with this brush and moved to the sphere. And on the surface of the sphere, we have lots and lots of charges accumulating. And then, as we said, as soon as there is so many that, there's just no more place for anything else to put down, there is a discharge to this other sphere. And I can tell you that I can't wait until we can get back to the library where Ms. Casey is usually hosting us, and where we can bring our Van der Graaf generator, and we have every kid stand on a step stool, put their hand on the sphere, and we have y'all's hair rising up. So stay tuned for hopefully the next season at the library. All right, and that brings us to meeting our Maglab electrical engineer. At the Maglab, we do a lot of science. We build magnets, we do materials research, but mostly for our resistive magnets and for our superconducting magnets, we need experts that help us deal with the electricity that goes in those. And Ms. Sujana is one of those experts, and I'm super excited you're here tonight.
It was good joining here. I see that the kids are so excited and looks like they want to join in. I see them answering everything and they get everything. Yeah.
Yeah, but it's super exciting. So Sujana, tell us what you do at the Maglab.
So I guess I work with, as you said, we have a lot of departments that we all work together as a team. But what I do is I work with the scientists like Yulia. So they have a lot of different ideas that they want to execute, that they want to design. They need help doing that. So that's where we come in as an engineer. We would help them try to put their ideas into reality so that we could know, like, if they have an idea and we try to provide a solution that works for them, and you can also see the result in a physical form. So in simple words, that's what we do here at the Maglab. And we also have users coming from all around the world to do a lot of experiments on magnets. So what we do is they might have issues with the instrument or with the machine, and they might need help in solving that. And that is also where we come in, try to help them out, make sure the experiment goes well. And yeah, that's, I guess, one way of thinking on what we do.
Yeah. Okay, thanks for that. And also I wanted to mention, I put up the questions here and I saw that Kristen put it in the chat. If you all have questions for Sujana, please put them in the chat box.
There's already some questions and they are such good questions.
All right.
There's a question right now. Is it possible to take all of the charge from an object?
Okay, I think I'll have a first stab at that. And Sujana, if you want to add in, please do so. So removing all the charge from an object is really, really hard because, you know, we are built up of atoms. Everything is made up of atoms. So what you can do is you can remove some charges, but there will always be some more left. So as long as there is an object, there will be charges. What you can do is you can, and as we said, most objects are, you know, neutral. So if you have the charges balanced in an object, there will be no effect from there being all those charges. So in that sense, if you have a charged up object, you can discharge it and you can bring it to your neutral state. And in that sense, you have removed the imbalance of charges.
I would agree. I wouldn't want to add anything more. That clearly explains it.
Perfect. Another question about maybe take these two together. Does absolutely everything have a charge? And does charge have a color?
All right. No, charge does not have a color. There is a little bit of a relationship between charge and color, which is that if certain atoms or molecules get excited and then they fall back from an excited state, they can be emitting a photon, a quantum of light, a little bit of light, and that will have a certain color associated with it. So there is, to some extent, a relationship there. But even though we drew our protons red and our electrons purple, I think there is no color to them in that sense. And remind me what the other question was?
Oh, does everything have a charge?
No, not everything has a charge. For example, neutrons don't have a charge. So there is particles, very elementary particles, that are not charged.
What about if you turn something off, right? Does it still have a charge?
I guess I'm guessing maybe the person is thinking along the lines of a radio or you know, a hairdryer or some sort of electrical appliances. And maybe that's something that Sujana wants to talk about, that there could be capacitors that may hold a charge or
not for long. So I guess the question was, so can you please repeat the question?
Sure. It says, if you turn something off, will you still have a charge? And it kind of connects with this idea, this other question that someone just asked too, that if a person touched something full of charge, right, what would happen? So those are kind of maybe related. You could take them all together.
So I think for certain circuits, like if they are capacitors in a closed loop of that, if they are capacitors, because capacitor is nothing but it stores the charges for a certain amount of time. It is not like a battery where the charges are always there. It's like you have the energy for a certain amount of time and later on it discharges it. So in in a way that yes, they may be a charge, but not for longer period of time. It takes some time to discharge it, but after that, no, you wouldn't have any charge on it.
I think we can generally say that, if there is no mechanism keeping it up, it likes to become neutral.
Yes.
So neutral is the preferred state. Neutral is the preferred state, just like me on the couch.
Yep.
Yes, exactly.
Yep.
Love it. Love it. So there's a great question about if you broke an object with a charge in half, would the amount of charge reduce by half per half?
I guess it depends. I wouldn't say exactly half. It depends on what kind of material, or if it's a metal, that's a different thing. If it's an insulator, that's a different thing. So I wouldn't say it would exactly be divided by half. I would say it depends on the material, definitely.
Okay, awesome. There's a question about how do you create a charge if you start with no charge? Would you transfer it from something else? Talk a little bit about that.
I guess how Julia said, so if two objects are placed together, inherently one object kind of pulls the other object's electrons. So one object might be inherently more attracted to electrons than the other one. So it can pull the electrons from the other object. I guess that's the question. Would it be able to so that's the question, right?
I think so, yeah.
Yeah. So what was what was the end of that question?
If you can transfer charge from one place to another.
Oh, so if there is no charge, like if you have two objects, obviously one would be electrically more attracted towards electrons, the other might not be. So that's how you can have that imbalance, as Julia mentioned. So then obviously you can transfer the charge from that object to the other object. So that's how you transfer the electron. I'm sorry if I got the question wrong though.
No, I mean, that's how I looked at it. Yeah.
Yeah.
I think that's going okay.
There's a question about which is stronger, protons, electrons, or neutrons. And I don't know exactly what's meant by stronger, but I would just say take that however you want to take it, ladies.
So in terms of charges, a proton and an electron are equivalent, but the opposite flavors. And then the neutron doesn't have any charge to it. So if charge is our unit of strength, so which one is the most charged or the strongest electrically, the proton and the electron have an equivalent magnitude of charge, and the neutron loses, it's neutral, nothing there.
Awesome. And I'm going to put a link in the chat to a fun activity we created a few years ago called Pancake Particles, where you can learn more about electrons and protons and photons and neutrons. And you can actually take like little cutouts of them and bring them to places around town where, you interact with their prevailing subatomicness right out in the world.
Awesome.
Yeah.
I want to say that I see a previous question that wasn't answered sometime before. It was from Rose. She asked, how do you know that you wanted to learn science?
Yes, I was going to come back to it. I was going to come back to it after we talked about electricity a little bit more.
Yeah. If you want to do that, that's fine.
No, please take it now, right? This is an amazing question. How did you know you wanted to be a scientist and engineer? What was your path to science and engineering?
So that's kind of interesting, actually, because obviously, as a kid, I was very curious on how things work. I just want to know everything. I used to always ask questions and whatnot. I'm from India, which is a different country than USA. So the things are done a bit differently over there. We have a lot of importance already given to math and science. So that kind of made me more inclined because the teachers are always there telling you what can happen if you go through this path, or how interesting, like they were the ones, because there was always an interest in math and science. The teachers used to always say, this is how you need to do the and they would bring you all these hands-on experiments to classes as what you're doing right now. And that kind of made me curious to know what all that we can do. And this feels, I mean, even though you're learning, this seems to be so much fun and so cool that you can do all these kinds of stuff. That's what I used to think when I was a kid. I would be like, what is this stuff? Like, how are people doing all this? So yeah, I would credit my teachers, because they were the ones who were like, showing us all these cool experiments, saying that, hey, we all can do this. Like, you know, you can still be cool and still get to do a lot of fun stuff, and as well as you're learning. So I would say that is how made me inclined to go towards science.
And I really resonate with what Sujana said about, you know, having so much fun, because I still feel like when we go to work, and Sujana and I work together a lot, it's almost unjust that they want to pay us for having so much fun.
Yep.
So yeah, it's, you know, I guess as a scientist or engineer, you can keep this this curiosity that we all come into this world with, and you just keep fostering it, and you keep fostering asking why and how and can we and why not. And yeah, so we get to play a lot.
Yeah, I agree. And also we get to learn new stuff even now, even though it's like you're always learning, but then it's always play also. It's not just learning, you're playing as well, in the sense you get to learn new things, but you're doing it in a cooler way, I guess. So yeah.
I love that answer, and such a great reminder about paths to science and how different they are and how similar they can be. And they do have a lot of fun at work, I have to tell you. So, you know, one thing I wonder, it hasn't been a question exactly, but there are a couple other questions I want to ask on behalf of our participants tonight. There's a question about whether the amount of charge we have in our body changes when we sleep. Do you guys know?
So I would say, I guess, because you are still in contact with the bed sheet, your pillow, and so that actually, it's kind of the same thing with the balloon, how once you keep rubbing, your hair kind of lifts, right? So sometimes if your material from the pillow is, like, if you rub it a few times, you can actually feel your hair sticking up. So if you're sleeping on a place where you're in contact with all these different environment, I suppose. So yeah, I wouldn't say it would be zero. There is still an exchange of charge between you and the pillow, you and the blanket, because sometimes if you remove your blanket super fast, you kind of feel that zap. So yeah. So I wouldn't say it's entirely, I mean, there would be some change depending on where you're sleeping, on what you're interacting with.
Yeah. It's like the same effect, like sometimes when you get out of the car and you like have a certain pair of pants on and you pivot on your seat and you get out and you're like, what was that? Yep. So the charges on you changed.
Yeah, or like your shoes, if you kind of scuffle on certain surfaces, you can get a little jolt. So there's a question about from a panelist about if I were a charge, which one would I be? So I guess maybe we'll just pose this to you. If you two were a charge, Julia and Sujana, which charge would you be?
Okay, if I was a charge, even though I am a very positive person, I would definitely be an electron. I would be a negative charge, just because the work that we do at the lab is electron based, and so I would be an electron, but I don't want to speak for Sujana.
I agree. It kind of makes sense. I wouldn't say positive and negative works both ways, because they are the same thing but in opposite directions. So both probably for neutrons.
I love it. I love it. We actually had a whole battle about this several years ago. We'll have to recreate the subatomic smackdown specifically for Science Night, where people can decide which one they identify with or love the most. There's a question actually about the Maglab and electricity. And the question says, what projects have you done at the Maglab involving electricity? But, you know, I work at the Maglab too, and I know the Maglab has a very complicated relationship with electricity, right? And electricity and magnetism are, we'll talk about that, right?
Yes, they are very coupled, and I don't know that there is anything at the Maglab that we've done that has not involved electricity. But you know, thinking about the big magnets, I think the big science, I guess we really pump a lot of electricity. It's about, like, on a good day, 7% of all the power used in the city of Tallahassee. We pump that into our magnets to make super duper high magnetic fields. So that's probably the biggest power, highest electricity project. But as Kristen said, electricity projects range from the itty bitty tiny little electron microscope pictures to the super big magnets.
Yeah, I agree. I guess it starts with lighting up a small LED to all the way till trying to improve our power. That's what, like, currently we are working on this project where we are trying to increase our current capacity of these huge big power supplies. So yeah, it ranges from small thing to the biggest thing in the Maglab, and everything involves electricity and magnetism and all these basic principles. So all around in every nook and corner of Maglab, electricity is like it's in the forefront of everything that we do.
Yeah.
I love that. Yeah, we often talk about how electricity and magnetism are almost like two sides of a coin, right? Right, ladies? Like when you have one, you kind of have the other. And in fact, you know, if you're watching the Science Night, right, powered by electrons,
Right.
So there's a lot to love about the noble electron, right? So there are a couple other questions. This is clearly a very interesting topic. People have lots and lots of thoughts about this. Would there be no electricity if we removed protons or electrons?
I would go a step further and say there would be no us. Yeah.
Because atoms are inherently made of electrons, protons, and neutrons. So we are made up of atoms. So everything in and around surrounding us is made of atoms. So yeah, I agree with Julia. There would be no us.
Amazing, isn't it? I mean, we're talking about big stuff here, guys. Could one of you explain, or both of you explain, how electricity travels across space? For example, how lightning goes from the cloud to the ground. Are there limits to the distance that electricity can travel like that? Maybe talk a little bit about that.
Limits to the electricity. I mean, it can't be infinitely far. It needs a space to travel to. So I guess it's about the amount of charge build up and the distance, so that it can create what we call a breakdown or have a discharge. So yeah, I think that's how I would express that.
I agree. Like, in the sense of, so I guess the question is if there's any limits in the distance on how, so what I understand is that for you to have an attraction, it needs to be in a certain, because each metal or each, I guess, each object has different kind of, it's made up of different number of electrons, protons, and neutrons. Not every object has the same number of electrons and protons and neutrons. So the amount of attraction one object has on, like a metal having on another metal versus a metal having on an insulator is different. Like example, an aluminum having an attraction towards another metal, like a gold or copper, is completely different from an attraction between aluminum and wood as an insulator. So it's like, it depends. I would say yes, the distance plays a role, because you need to have that force of attraction, but that distance would be a long way away, but you still need that so that you can attract the electrons from that different objects towards yourself. But it depends on the material that we are working with to know what distance or what force of attraction is playing a role there.
Excellent point. Always a lot of factors, right, that you guys are thinking
Yeah.
about as scientists and engineers, and
Yep.
usually to manipulate them, right, so that we can make happen what we want to make happen, right?
Mhm.
Right.
Yep.
Well, we call it controlling parameters.
Different variables.
There's some questions about what has a charge. Does a couch have a charge? Do magnets have a charge? What has a charge?
So I guess this comes back to everything being built up of atoms. So there is the building blocks in it to I guess exhibit being charged one way or the other. Specifically for the couch, you can do an experiment and you can sit on your couch and kind of wiggle around and see if you can get a discharge going, or you can stick a balloon to your behind after. So yeah. So there are plenty of charges. It just depends, I guess, where we push them.
That sounds like a fun science experiment, and you can report back, everybody.
Yes.
And there's another question about whether we can see individual electrons, protons, neutrons with proper equipment.
Okay. That's a little bit tricky. So we can see very, very small things. However, it becomes hard to see things directly. So we can, with proper equipment, we can see signatures of certain particles, and we can say, you know, this is particle, but you can't take a picture and, you know, say, hey, look at my pretty electron. So yeah, we can, I guess I would say we can visualize them.
But not exactly, I suppose. Like,
Yeah.
yeah, it's just, yeah, it's I guess it's hard to say. Like, have I seen it? I would say no. I haven't seen it, but yeah.
But maybe we can mention that, for example, we do, we do measure charges, we do measure electricity, but I would, more the bulk of it than the individual.
Yeah, and I know that lots of scientists at the Maglab, right, are using the powerful magnets to understand kind of those electronic properties of materials, right? So they're looking at different measurements and understanding how the electrons change based on field or temperature or pressure, all those sorts of things. So, not like a picture, but they're looking at some measurement to make that assessment, right?
Right.
And go ahead, Yulia, I'm sorry.
Yeah, and it's to me as a scientist, it's always fascinating to see it seems like the smaller the thing is we study, the bigger the machine becomes that you need to see it.
Yes.
So, particle physics, all these tiny little particles, you need these huge accelerators. And then, as Kristen said, we study the electronic properties of materials because really the electrons rock the show for most of the properties. So, we have these huge magnets, gigantic magnetic fields, a whole facility full of equipment to make all of this happen. So if you come to the Maglab, and we hope that'll be soon and you can visit us again, we have a huge plant, we have, buildings full of equipment, and then people come with their sample, which comes in these itty bitty little boxes. So, to me, that's just fascinating.
Yeah, and we actually have a great video series. I'm going to put that link in the chat too, where if electricity, magnetism, these things are indivisible, right? We can't see them with our naked eye, but we actually did work with a few animators to help us visualize, like, what would it look like if you could see electrons moving through wires or all sorts of things. I'll put a link to that in the chat for those of you that want to get a stronger visualization of electrons and all the cool stuff that they do. There's so many questions, ladies. I'll just keep asking them if you'll let me, but I don't know what time this party wraps, but
I think we have to wrap up soon, but maybe one last question.
Okay, let's see. A question about, does gravity affect electricity? Do electrons bend around planets? Kind of a linked question.
Let me think about that. I would say that there is an interaction, but I don't know that I have a great answer to explain it.
Yeah, I would say it would. I wouldn't say it would affect the electricity in the sense, not electricity, but we are made of mass. Our mass are again is atoms. We are also made of atoms. So inherently it is kind of affecting, right? Like if you're what you're made up of is changing with your interaction with different objects, does that mean that gravity is also showing its effect in the sense how the force of attraction is between the two objects? I can't clearly say it does or doesn't, but I would think maybe in certain amount it does affect, right? What do you
I
think,
think,
Julia?
Sujana, what you're saying is right. And I think if we rephrase the question a little bit in the sense that we say, is a charge, like rather than electricity, if we move it into a charged particle, a charge, then we can definitely say, yes, it is affected, because you're basically, you know, with a planet, you're looking at a really, really big mass, and then your charge is a really small one, but there definitely is a gravitational interaction. Electricity is a little different of a concept, where it's, you know, more of a flow of mini charges together.
Electrons,
So yeah, I think if we meant like that, I think we're good.
I love that. I love that. And ladies, just before we wrap, I just wonder if you could kind of articulate, we've got probably, you know, we took the age range of our participants, and, you know, some of them may not understand the difference between being like a scientist and an engineer. So could you guys just maybe articulate a little bit of that for yourselves? Like, Yulia, like, why did you pick like science? Like, what do you think it means to be a scientist versus an engineer? And Sujana, the same for you. Like, what kinds of things does that mean you do that are different from maybe, you know, a scientist path? They're both amazing paths. It's not a competition. They're both fantastic. Just as they think about growing up, and those can be different routes, right? So maybe just cover that a little bit.
Right. Well, so for me, I'm a scientist, I'm a physicist, and it's actually very similar to what Sujana said. Is, you know, I was a curious kid. I wanted to try out things, always wanted to know why, and somehow never lost it. And I always enjoy, you know, the exact sciences, math, physics, biology, and all that stuff. So being able to do that for a job, you know, keep on playing for a job is just amazing. So, you know, as a scientist, we try to answer very fundamental questions, sometimes also more applied questions. And I think that's where we kind of blur into being engineers. I think there's a lot of overlap, especially, you know, for me, I think I'm about as close to engineering as a scientist as one can get. I think there's a little bit, I always feel like there's a difference a little bit in the sense that, you know, engineers are super duper trained in doing stuff, building stuff, and getting it done, while the scientists are sometimes a little bit more on the philosophical question side of like, you know, what do we need to be investigating, and, you know, those kind of things. But I think especially at the Maglab, it can get a bit of a blur. Yeah.
Yeah, I would think that science is behind both scientists as well as engineers. That's the fundamental. So when you are as a kid, you don't have to worry if you want to be a scientist or an engineer. You could just base off everything with science. As you reach at one point, you would know how much you want to learn. Like, are you interested in building stuff, or are you interested in knowing the fundamentals and why they are the fundamentals in building? Like, you know, we say that electricity, magnetism, these all are the fundamentals, but only few % of people really know why they are and why it is coming into our existence, why we are made up of atoms, and why. I guess I would think that scientists are the people who really wonder why, and they try to get behind these basic principles in understanding on why we are learning this, like why, like they are trying to understand the universe. Engineers are more like they try to apply what basic principle the scientists are inventing or figuring it out. They apply these principles and try to build stuff so that they can make our lives easier. Like like 10 years ago, they weren't the phones that we have right now are so advanced from what they were even 10-12 years. So that's all engineering, but I wouldn't say it's just the engineering. It's a combination of research that is done by the scientists where the engineers help out in trying to apply that understanding into a physical device that makes all of our lives easier. That's how I see it as this. But I would say if these kids, they want to really just concentrate on science, and they will be good at later on once they understand where they want to go, if they want to do more research, or if they want to understand more, or if they want to build stuff more. I guess it's up to them. But yeah, as Julia said, it's an interlap and overlap. So yeah, especially with Maglab, it's all a team of different sets of people from different fields trying to work together. Like there's materials, there's resistive magnets, there's superconductivity, and all these people are, they're different scientists in different fields and different engineers in different fields. It's all of them coming together. So yeah, I guess the parting answer is that science is behind everything. So I guess if we are good with that, we are good with where we want to go.
I love that. I love that answer. Thank you, ladies. I think about that a lot at the Maglab because sometimes I'm halfway into a conversation introducing someone as a scientist and they're like, no, I'm a biomedical engineer. I'm like, oh, I had no idea. And so I think that the big takeaway is that, these are very related disciplines and are both extremely important in pushing our world forward, right?
Yep.
Exactly.
Agreed.
All right. Well, thank you so much, Sujana and Kristen. And please hang around as we pass this to Ms. Casey for the library picks.
Hi, everyone. Oh my gosh. It was such an awesome science night, learning all about electricity and all about Sujana and all about Yulia and why they chose the career paths that they chose. Oh my goodness. And it ties into the library too, because we answer questions and help you get on the path to be what you want to be. And we help you find fun little experiments here. I don't know if you can see my book. There it is. Projects with electricity and magnetism, if you're looking for those science projects that they were talking about. We have a book about You Wouldn't Want to Live Without Electricity. Electricity has always been around, but this book tells you how we learn to use it. And let's see, I don't think you can see that, can you? So let me take this off here. This book will tell you how we, there we go, how we used it and how we managed without it in the past. So that's a fun series there. You wouldn't want to live without. And of course, you can't talk about electricity without our friend Pikachu. Yay. Yes, I see Suju going Pikachu. Yeah, so Pikachu and electricity. I always bring like a fun book for you guys. So you can find all of those at your LeRoy Collins Leon County Public Library system.
All right. And if you want to check out Ms. Casey's book list, check out our Science Night website. And you can click on book list and it's right there. And I know that at the bottom of the list, it even tells you how to get a library card if you don't have one yet. All right, that brings me to the end. It was super fun to hang out with you guys tonight and talk about static electricity. Please come again next April, the 22nd. Our topic will be optical illusions. It's our last science night of the season, and optical illusions is one of my favorite ones. It is a lot of fun. We also have a fun hands-on activity. So please join us. And that brings us to closing remarks. Kristen, did you want to point out any resources?
Oh, I've put so many resources in the chat for you guys. I hope you go check out all those videos and additional, opportunities on the Maglab's education website to explore pancake particles. I'll make sure to post them all in the Facebook event page too. So if mom and dad responded, that you can find all those resources there as well as of course Miss Casey's book list. So.
All right. Well, then I thank Sujana, Kristen, and Casey. And we also would like to thank our sponsors. The Maglab is sponsored by the National Science Foundation and the state of Florida. And that makes all you stakeholders in our science. So thank you very much. You guys stay curious. And we hope to see you next month. Thanks a lot. Bye-bye.
Thank you.